CFL is quite obsolete nowadays, which are undertaken by the much more efficient LED bulbs, but it's quite good to know how its electronic ballast works. So, I took this old bulb apart and soldered a plug for the mains so we can plug it later. This is just a cheap crappy CFL brand, so it's not that high quality, but it still follows the same working principle. Basically, the mains is rectified to DC with this full bridge rectifier, and this is the smoothing 400 volts electrolytic capacitor. Now, these are the two switching high voltage NPN transistors, and there are some series capacitors in the output going to the tube. And this is the output inductor. It looks like a transformer, but actually there's only one winding on it. Beside it is this toroidal transformer, which is used for feedback to properly drive the transistors. It has also a current limiting resistor for the transistor, and this small electrolytic capacitor. There's also a resistor probably responsible for starting the oscillation, and the CFL lamp still works. It may look crappy and old, but this still works. Reverse engineering time. And this is the schematic. I reverse engineered it and drew it on LT Spice. First, the mains is rectified through this bridge rectifier and charges this capacitor, which smoothens the voltage, so we now have approximately 337 volts DC, which is the peak voltage of 240 volts AC. I just put a 337 volt source in for our simulation. Okay, so just like an engine, there will be a small starting force to start the oscillation. At first, none of these two transistors is turning on, but there's a startup resistor going in this path, so the current will flow through this slowly, and what will happen, this line will be pulled up, but then there's a high value resistor here that will slowly charge this electrolytic capacitor through this path, and then the voltage reaches 0.7 volts. We know that this NPN will start to conduct, resulting to pull this line near to 0 volts. By running the simulator and probing on this line, we can see it's firstly pulled to high, then near to 0 volts. And see the base voltage go higher as it slowly go to the saturation mode. What is this capacitor doing here? Why not just connect it directly to the base? This is because if you connect it to the base, this winding had a low impedance to ground. The current will just go here instead of here. What about this diode? Well, let's try to remove this diode and start the simulation. It kind of starts at first, but see, the oscillation dies out in just a couple of milliseconds. You will understand this diode later on. Next, we are now charging these inductors in this polarity, storing the energy on its core, primarily this bigger inductor. So that means when this is positive, the other winding with this dot is also positive, so it will give current for the base, so this transistor will keep turning on until the polarity will reverse. Why will it reverse? Because this inductor, you can see it's connected to the filament of the tube, and then this capacitor going to the positive supply. We know that if we combine a capacitor and inductor, just like in this circuit, it will resonate. When we latch it to a supply now, see, it will ring, and we see the reversing of voltage in the inductor. So previously this is positive, so it will now be reversed. Because this coil is magnetically coupled on these windings, this will be also have a positive, So this upper transistor will turn on. And in the opposite side, this is now negative. So this transistor will be off. So the polarity will reverse again, so we have now an oscillation. So if we probe on the windings, these are their phase difference. This winding is in phase and the upper is 180 degree out of phase. For a couple of milliseconds, this oscillation will generate a high voltage across this capacitor. And the fluorescent tube needs this to start and arc over to the other electrode. Gases and mercury inside the tube will be even more conductive, so the main current path now will be here instead of here. So now, the tube is illuminating. By the way, the use of this diode is to protect the transistor from reverse high voltage spikes. So this will keep it safe. And these resistors are for limiting the current. But this diode, remember that this winding is producing alternating current, right? So when the current go like this, it will charge this polarized capacitor from positive to negative, right? So during the reverse, this capacitor will discharge because the current running through it is reversed. So that is the magic of this diode, to charge this capacitor. So if no diode, meaning it will just discharge and discharge until no energy is left, so the oscillation dies out. Now, basically, this circuit is producing a square wave with 50% duty cycle. In order to sustain the oscillation, the output is passed to this transformer for feedback. The nominal voltage, by the way, across on this tube will be from 100 to 175 volts, after having much higher voltage, about 600 to 900 volts. There are also another circuit variation, like on this 22 watt ballast. The difference is that this utilizes a diode for the startup. Commonly, they use this DB3 diode, which has this breakover voltage. Now, here this startup resistor will slowly charge this capacitor, but as it reaches to breakover voltage, a current will go through these diodes to the base of this NPN transistor, therefore starting the oscillation again. I also tried a real-world measurement of the circuit, so I inserted 2 turns of wire on the transformer and on this inductor, and hook it on the oscilloscope. We can see the similar waveform which will drive the base of the transistors, and the other one is the inductor. The frequency is 27.78 kHz. This high frequency, by the way, is important because CFL lamps tend to produce more light from 30 to 60 kHz, giving better efficiency. In our case, 27.78 kHz, which is not bad. It's quite acceptable. But the safety of this lamp is not that acceptable because it has no current limiting resistor or just a fusible resistor on the mains. An interference filter should be required because this produces high frequency electromagnetic noise and this will scatter everywhere. It should look like this. If you like this video, please don't forget to hit like, share, and subscribe. This is PinoyEngiNerd. I will see you later.